All right, so we've been talking a lot about finding zeros for polynomials. So now's a good time to start to talk about how to graph polynomials. As you get through to calculus, this is a pre-calculus topic, you should be able to reconstruct a graph that normally you would have been asked to use a graphing calculator for, but in calculus with certain tools, you should be able to sketch some of these graphs without that. And so we'll talk about in this video how to sketch some basic polynomials to get the general sketch of a polynomial. And a good place to start here, all polynomials will have at least one x-intercept. They're going to cross the x-axis at some point. Most likely, I shouldn't say all of them, but many of them do. The ones that will ask you to graph, how about that? And so there's an interesting thing about x-intercepts, and this is not only for polynomials, but for other functions that we'll see. Whenever you're looking for the x-intercepts of a function, remember to find the x-intercept, you would be setting y equal to 0. You'd be setting, in this case, x squared equal to 0, which gives you x equals 0. If you were finding the x-intercept for f of x equals x, you'd be setting that equal to 0, and that's already it. Notice that all of these polynomials have the same x-intercept, which is 0. When you set these equal to 0, that's your one and only answer. But there's something interesting about how the graph behaves as it gets near or at the x-intercept. Okay, here's f of x equals x squared. We know that's our familiar parabola. Notice that the graph, if we go from left to right, hits the x-intercept and rebounds off. Y equals x, or f of x equals x. As it goes from left to right, it goes to the x-intercept and it goes right through it. F of x equals x to the fourth. That's just a more steep version of a parabola. It's not really a parabola, but it would just it would look very similar, but a very steep curve. But notice this one, I would say that the x-intercept from left to right, it hits the x-intercept and bounces off, just like f of x equals x squared. The graph of f of x equals x cubed has an x-intercept of 0, and it just keeps on going through. That looks like it's not a great graph. It actually does not hug the x-axis for that long. It only touches at 0 and then goes up. So this is what I would classify as going through. I've got a couple more. If we have f of x equals negative x to the sixth, f of x equals x to the sixth would be an even steeper version like x to the fourth going up. But of course, if it's negative, we know that's going to reflect it down across the x-axis. But what about the x-intercept? From left to right, it goes up to 0 and bounces off again. Negative x to the fifth, the graph of positive x to the fifth would have looked a lot like f of x equals x cubed. It would have been a little bit steeper. And of course, the negative is going to reflect that. So this part goes down, this part goes up. And again, it's a little steeper. But in terms of the x-intercept from left to right, 0, and it keeps going through. So you probably noticed something. All x-intercepts, they are either going to bounce off the x-axis when they hit it, or they're going to pass through. And what does it depend on? So all of these in the left column, your x-intercepts come from even powers of x. So the graph, I use bounces off or just bounces. Other books use kiss. They just kiss the graph. They just touch it, kiss it, and leave. I like bounces off after hitting the x-intercept when it comes from an even power. If you're setting an even power equal to 0 to get your x-intercept, you can be assured that your intercept is going to bounce off the x-axis. Whereas all of my graphs on the right column, x to the first, x cubed, x to the fifth, these x-intercepts go through, goes through. Other books call it cross, which is fine. It crosses the x-axis, whereas these kiss the x-axis. And how you can tell your graph is going to pass through the x-axis is when it comes from an odd power. And this little fact is actually very, very useful. And really one of the only tools we have to get a reasonable sketch of a polynomial graph without knowing more calculus. So let's practice this. Without using a graphing calculator, we're going to give a rough sketch for some polynomials here. And so what I want to know is my x-intercepts. And so to find my x-intercepts, I'm going to always set y equal to 0. Here I can factor out an x squared. So I get two x-intercepts. One of them comes from setting x squared equal to 0, which gives me x equals 0. The other one comes from setting x minus 4 equal to 0, which gives me x equals 4. But what you would want to do next is then classify one of these intercepts goes through the x-axis and the other one bounces off the x-axis. And so what we learned on the previous page, this 0 came from an even power of x. So this intercept is going to bounce, whereas this 4 came from a factor that was to the first power, which is an odd power. And because that's an odd power, this one's going to go through. So I know I have an intercept at 0. I know I have an intercept at 4. We'll write it as 4, 0. And the way polynomials work is they always, if you move in the positive x direction, they always go up to infinity or down to negative infinity. Same thing in this direction. They always go up this way or down this way. So I know this intercept goes through, the graph goes through here. So it's either going to do that from left to right going up, or maybe it's coming down like this, right? It's one of those two. So what I could do if I want to figure out whether it's going up or going down is I need to see where my function is at some x value bigger than 4. And so what I could do is just pick a test number. Let's say pick a test number. So for example, I'm going to pick 4. I'm going to pick f of 4. And what I want to do is decide whether not f of 4, something bigger than 4. I want to pick f of 5. Something bigger than my largest x-intercept, because I need to see if it's positive or negative. Now, of course, I can plug in 5 into my original function, but oftentimes when you're plugging in functions, it's easier if you plug it into the factored form. So f of 5, I can tell if I plug it in right here, because that's the same function, is going to give me 5 squared times 5 minus 4. That's 25 times 1. That is positive 25. So I know that a point on my graph up here is 5, 25. And that's actually all I need to know, because I know the graph is going up in this direction. I know this intercept was through. If I sketch it now from right to left, at some point it has to come back around and hit this intercept, right? This is 0, and we know that's a bouncing intercept. So when it hits it, it's going to bounce off. And once it bounces off, since there aren't any more x-intercepts, we can be assured it's just going to continue on down. One of the things if you do homework from one of my classes, I say, give a rough sketch, and I say, don't worry about how high or low the graph goes in between x-intercepts. We don't know, I don't even have a scale here, right? I mean, how do I know if this goes way down here or if it just barely goes down below the x-axis? That part I don't care about right now. We'll figure that out. We need to know some calculus to learn that, to learn how to figure out how low it goes. So don't worry about that right now. It's just a general sketch. Let's try another one. Okay, f of x equals x to the 5th minus 8x to the 4th plus 16x cubed. I want to find my x-intercepts. I'm setting this equal to 0, and I'm going to do some factoring. Looks like I can take out an x cubed, leaves me with x squared minus 8x plus 16. And that factors into again into x minus 4, x minus 4. So one thing about this bouncing off and going through in terms of x-intercepts, if you do get an identical factor, then you need to put it together and write that as x minus 4 squared. So I can see that my x-intercepts are going to be 0 and 4. The 0 is coming from an odd power. So I know that this 0 is a through intercept. The 4 is coming from a factor that came from an even power, so that is going to bounce off. So 0, 4, we'll call that 4, 0. Same idea, I need to know, okay, I know it's a polynomial, so I know, well, this one's bouncing, so it could be bouncing above here, or could be bouncing below, right? We don't need, no, but what would answer that question is if I pick a number bigger than 4 again, in this case, if my graph's up here, then I know it's going to be bouncing from above. If my point is down here, then it's going to be bouncing off from below. So once again, I would probably pick 5. So let's try f of 5. To be good, easy, I would plug it in right here rather than in the original function, because that's going to take some time to work that out. F of 5 is 5 cubed times 5 minus 4 squared. 125 times 1, so it's a positive 125. Don't worry about a scale. It's somewhere up here, huh? It's 5, 125. If you get something on your homework where this number is huge, you could even just put 5 big positive. I don't really even care that you give me that exact value, because we're just going for a general sketch. But now that I know the graph is up here, I know it must have been going up to infinity. If I go from right to left, it must have bounced off this one, gone up a certain amount, right? We don't know how much, but then it's going to go through this intercept. One little thing, if you really want to get a more detailed graph, yes, my intercept is going through, but if you go back to that first page, the way it works is if you have an odd power x-intercept that comes from any power 3, 5, 7, what always happens is it comes in flat. It comes in kind of horizontally and then crosses. The only one that just goes straight through the intercept is if it just comes from x to the first power. So what I'm getting at here is this 0 came from an x cubed, and so it actually goes through 0 looking like an x cube. It actually gets flat a little bit and then goes down like that. If you just draw it straight through crossing like that, I'm totally fine with that. But if you really want to get a detailed graph, so when you check it on your graphing calculator, you're going to see there's this little flat point right here. Okay, a couple more. Try to graph this as a 4th degree polynomial. We want to find our x-intercepts. I don't really like factoring when my leading coefficient is negative. So what I would do is factor out the negative. That's x to the 4th minus 13x squared plus 36. And something we talked about earlier, this has quadratic form, doesn't it? If I remember this is going way back. If I let u equal x squared, this polynomial has the form of u squared minus 13u plus 36, which factors into u minus 4, u minus 9. So putting back in my x squared, that factors into x squared minus 4, x squared minus 9. Okay, I guess I should, there was really a negative there, huh? Let's make this all negative. Now, the other thing about this bouncing off going through thing in terms of looking at the powers, I'm pretty sure many of you could figure out that this is going to give me 2 x-intercepts, positive 2 and negative 2, and this is going to give me positive 3 and negative 3. But then the next thing we're supposed to do is look at the powers, and I don't want you to be fooled. You might be fooled into thinking that they're coming from even powers because of the x squared. So what you really want to do is, when you're doing this, is factor it completely. If oh yeah, I'm setting these all equal to 0. If I factor x squared minus 4 again, I get x plus 2, x minus 2. This is x plus 3, x minus 3. So I'm getting 4 x-intercepts. The negative doesn't matter, right? If I set If x is -2, everybody, this thing is going to be 0, the whole thing is going to be 0. So I get -2, +2, -3, +3. And they're all, in fact, coming from odd powered factors. So all of these are going to go through. Let's say this is -2, -3, +2, +3. And then what we're supposed to do is pick a test point here, right? One thing I didn't do on the previous two is an easy point to find, which we have talked about, is a y-intercept. I didn't do it for the previous two. Let me go back to those. And the reason I didn't find a y-intercept is because for both of my first two examples, one of my x-intercepts was 0. And 0 would be my one and only y-intercept. So I already have it. Same thing for this one, right? That was 0 was an x-intercept. But 0 is not an x-intercept here. And so an easy point to find is to just find a y-intercept. Remember, that's just the equivalent of plugging in 0 for x. And that's really easy to do. If I plug in 0, I'm going to end up getting -36. So that's like way down here somewhere. And truthfully, all you really need is one other point other than your x-intercepts. And if you get the through bouncing off idea, then you can actually sketch the graph. If you want to pick something bigger than 3, like we were doing before, you can do that as well. But here's what I know the graph's going to look like. I know if I sketch it to the right, I know I have to get down to this x-intercept, and I know it's going through. So it's going to pass through, but then it has to come back down and hit this x-intercept, which is also a through intercept. And once you're done with your last intercept, it's just going to keep going down. If I graph to the left, same idea. It's got to hit this x-intercept, go through, bend back down to hit this intercept and go through, and that's it. Keep going down. Something like that. Okay, one more graphing this way. And my point on this example is the previous one. I wanted to remind you about quadratic form, how you can do a substitution and make it look like a quadratic. Here, if you're going to try to set this equal to 0, remember another strategy we talked about for a cubic equation or something with 4 terms is grouping. Remember that? So if I group the first 2 terms, and then I have a minus there, and I'm going to group the second 2 terms. So that's going to be 4x. Remember, if I take out a minus, this is going to switch to +12. Because if I were to distribute that back, I get the same thing I had up here. If I factor out an x squared, I get x plus 3. Here I can take out a 4, which also leaves me with x plus 3. Then between this term and this term, I can factor out an x plus 3, which leaves me with x squared minus 4. And just like the last one, you would want to factor anything like that completely. X plus 2, x minus 2. So I get 3 x-intercepts at -3, -2, +2, all coming from factors to the first power. So once again, these are all through. Let's say this is 2, -2, -3. I guess I could find a y-intercept again, since that was, well, not one of my x-intercepts, was not 0. So f of 0 is easily defined that that's -12. So I know from the right, and this doesn't necessarily where it turns around, but we'll just make it look like that. It's going to hit this intercept, go through, and keep going up. This one's going through, has to come back down, go through, something like that. Okay, so we've done 4 here, where I've given you the equation to graph it. Another thing to be able to do, and watch out on tests where, other than asking you to graph it, is to give you the graph and see if you can come up with a possible equation for the graph. So you're kind of working backwards here. Notice I have 3 x-intercepts on this first one. I have x-intercepts of -2, 0, and 2. And notice they are all through x-intercepts, which means they must all come from odd power factors. So then if you kind of work backwards, you think of it this way. If I have a factor of -2, that means it must come from x plus 2. If I have a factor of 0, that just comes from x. And a factor of 2 must come from x minus 2. This is fine. It actually satisfies all of the requirements, meaning all these intercepts would pass through. But based on something I said before, remember, if the graph does go through in a flat way, that means that this power of x is 3 or higher. So you could use 3, 5, 7. I'm just going to go with the smallest number. How about x cubed? If you did not put that cubed and just left it as x, I would give you full credit on the test because it still does go through. This is just, again, getting really detailed. So this would be fine. You could leave it like that. You could, alternatively, you could multiply it out. Like maybe I would put that first. And if I multiply x plus 2 times x minus 2, that gives me x squared minus 4. And if I distribute this, that's x to the 5th minus 4x cubed. This is fine too. All right, last one. Good chance to practice. If you think you've got this, pause the video, see if you can find a possible equation for my last one. All right, let's try it. So we have an x-intercept of 0 and 3. The 0 is going through. And notice it's going just directly through, right? It's not flattening out like the previous one. So we know this one's just going to have a degree 1. It's just going to be just to the first power. Whereas my 3 is bouncing off. And so that must come from an even power. And in that case, you can use 2 or 4 or 6. We really don't know. I usually just use the smallest one. So as a starting point, a factor of 0, an x-intercept of 0 must have just come from x, and we agreed it would just be to the first power. If I have a 0 of 3, then it must come from x minus 3 to an even power, so that's x minus 3 squared, or 4th, or to the 6th. But then you want to make sure, you want to check on something here. Notice that on my graph here, if I plugged in a number bigger than 3, like 4, I'm going to get something negative on this graph. But notice if I plug in 4 here, this is going to give me something positive. So this is not the right equation. This would have actually given me an equation that would have been up here. How can I make it so that there's a negative number? I can simply just multiply this by negative. If I make it negative x times x minus 3 squared, then I can be assured that, again, if I plug in f of 4, I'm going to get -4, 4 minus 3 squared. I'm going to get a negative number, which would match up with my graph. So sometimes you got to watch out. You might have to add a negative in front to get the correct equation. All right, hopefully you know a little bit more about graphing polynomials, and we'll work on other graphs going forward.